Hello, welcome back to Ninja BAS. We shall discuss analog outputs, binary inputs, binary outputs in this video. We'll be discussing what are the types of outputs, inputs we'll be usually using in a BS application. So with no further ado, let's start with analog outputs. Analog outputs are voltage signals ranging from 0 volts to 10 volts DC. So these DC voltage signals try to control the fan speed, the pump speed, or the actuators on how much it should rotate clockwise or counterclockwise, depending on what your programming is. Now, the analog outputs need not necessarily only be DC voltage signals. It can be control current signals as well. So these current signals can vary from a range of 4 to 20 milliamps, where 4 can be your 0% and 20 milliamps can be your 100%, or vice versa, depending on what applications you're using. Now, when it comes to these actuators, these can control the dampers or valves depending on how or where or on which application you're using. So these actuators varies from manufacturer to manufacturer. So the manufacturer says, I'm building a actuator of mine which is controlled from 0 to 10 signal, and another manufacturer B says, hey, I'm building an actuator, or my actuator is controlled from 4 to 20 milliamp signal or current signal. Now there can be a manufacturer who gives out a actuator which has a selectable signal, control signal as well. It can be 0 to 10, 0 to 5, 2 to 10, and there are manufacturers who give you selectable switch. It can be rotatable dip switches, in where you can tell your actuator, hey, you're gonna get control from control signal which is to be 0 to 10, 0 to 5, 2 to 10, or 10 to 2, or 10 to 0, depending on where or which application you're using that for. Now the actuators, you just cannot control that from your control signal. Actuators are nothing but these stepper motors which you probably used in your college days, where a motor has actually to be fed with a power signal. So these actuators from different manufacturers can take actual power, or is to be fed with actual power, which it can be 24 volts AC, 24 volts DC. It can be 120 volt actuators as well if you're using that in US. And if you're using that in India, there are actuators which you'll have 230 volts directly fed to it, apart from your control signal. So that's pretty much about actuators and the analog outputs. Let's see a simple illustration how it is actually wired and how it reacts to your control signal on field. So to demonstrate analog output, I have a quick setup of a transformer, an actuator, and a controller to which an analog output is connected with 24 volts being supplied to the actuator. So as it denotes, this is right now in 0th position, and I'm going to trigger a 5 volt signal to this to see if the actuator moves to half its way. Alright, let's see if the actuator so as you can see, the dial of the actuator is going from 0 to
have the percentage what it has. So this is the half which we so as we discussed in the video, you can clearly see this actuator mentioning about this needing a 24 volts for its supply, 0 to 10 volts or 2 to 10 volts. And this is the selectable switch where you can see it can consider 2 to 10, 10 to 2, 0 to 10, 10 to 0, or it can act as floating as well. So this was a quick demonstration for analog outputs.
So now that we have seen how analog output works, let's jump into binary inputs. What are binary inputs? So as you know, binary is nothing but 0 and 1. So these are the two states of inputs which a controller recognizes when you say binary inputs. So how does a controller recognize 0 and 1? What does it mean in BS terms? What does a binary input mean? Or how is it obtained as zeros? Or how is it obtained as one from a particular equipment? How that thing is controlled and what does binary inputs give you and how do we use that in a VS application? So in VS terms, binary inputs are nothing but the status of a particular equipment which you are obtaining if that equipment is running, if it has stopped, or if there is a damper, if the damper is open or it is closed, if the valve is open, closed, something which says within two states. That's nothing but binary inputs. Now, the usual examples which we can give in the BS application, which we'll be using for binary inputs, is the fan status. If the fan is running or not, if the damper status, the damper is open or not, or few other alarms. Let's say you have a variable frequency drive running for a specific pump. How do you know if the pump is in fault? How do you know if it is in some high temp alarm? So that's the binary input which a drive gives back to your DDC control so that you know, hey, I have got a binary input saying this is in fault, this is in running status, this is stopped. So that's how you know what the equipment status is. So the devices which are used to get these things are for fan status, you'll use current transducers to get the binary as a binary input. For damper status, you'll use the end switches. I'll show you how these things work, how it is wired back to the controller, how controller knows that, okay, this is running, okay, this is not. So the way the BS controller understands 0 and 1 is through the voltages again. So you have a closed circuit which is being fed from the controller itself. If you break the contact, you're gonna get no voltage back to the loop, the control loop, the voltage loop is not closed. So the controller will know, hey, I'm sending a voltage signal or a current signal from my voltage source, and I'm not receiving. The circuit isn't complete. So it might be it is open somewhere. If it is open, that's considered zero. If you close the same contact, the circuit closes and there is the full flow of your current throughout the circuit, which reads it is generally in the DC according to how the controller is manufactured. It is generally a DC voltage which is being fed, a minute DC voltage which is being fed, which has to flow through the loop and come back so that it recognizes Okay, the circuit is complete or the loop is complete, and that is considered as one. So zeros and ones are being fed with a contact which is open or which is made. Once you have an open contact, that's considered zero. Once you have a made contact or a normally closed contact, that's considered a one. In the programming terms, you can still define a normally closed contact as zero and normally open contact as one. So I'll give you a specific example for that. Once we take a binary input for, let's say, a fire alarm coming from a control module of a fire alarm system. So that is considered usually normally closed, which we consider that is to be normal. If in case of fire alarm, the contact breaks from the fire alarm guy. Once the contact is break, we know that, oh, the contact has broke and we have to shut down all our equipment accordingly. And that's how the hardware safeties are done. Once the contact is broke, the, the voltage passing through will be interrupted and all your dampers and everything will be shut close. And that normally open contact or the open contact from normally close is considered to be one for you guys, which is supposed to be zero. So that's how it works. You can deal with zeros and ones depending on what your application sees, and that's pretty much the binary inputs. Uh, let's see with a physical device, how do you usually get a binary input to your DDC? Let us see that illustration physically on the field. So for the binary input, what we have is, as you can see, one single wire coming from 20-volt DC going out and another wire coming as digital input or a binary input here. So what I have is the other two ends of those two wire open here. So as you can see, if I connect these two, you can see a light blinking right here, which says, hey, the circuit is closed. This is open. The circuit is closed. This is open. So that's what binary inputs is all about. I just to show you guys, I'll give you a closer look at the terminals here where it shows 20-volt DC going through this terminal out and a digital input coming back in. Once the circuit is complete, you'll see a light lit, which is state 1, and this is state 0 when the light is not lit. So let's start with binary outputs now. Binary outputs aren't the same outputs, or it is the same inputs which we dealt with binary inputs. It is still the same, just being an output from the controller, not an input to the controller. So binary outputs are still two-state output, which is 0 and 1 to whichever you have programmed it to be. Do you want the fan to be run? You state it to be at state 1. You don't want the fan to run, then you state your in your program to be at state 0. So making your programming at 0 and 1, what usually happens in the controller is when you say, hey, I want my fan to run, I'm sending you a 1. What the controller thinks is, I've received a command for 1. All I have to do is, if I have 8 outputs in my program, the controller thinks, okay, which program or which output has he set to be 1? So that particular output, the controller energizes the coil for that relay, to which it makes or breaks the contact within the controller. So that's pretty much the application what it does. When a binary output is energized or triggered, it energizes the coil, which either makes a contact or breaks a contact according to however you guys have wired it on the field or however the manufacturer has intended that controller, if that's a normally closed contact, normally open contact. So that's still varying from a manufacturer to manufacturer, what he has intended his controller to be and how you guys are actually using in the field to your application. So in a nutshell, all binary outputs are relay outputs. Rating of these contacts may vary from controller to controller. Some may take only 2 milliamp or 2 amperage of load. Some may take 25 amps of load, depending on what it is being used for. To trigger the relay or to trigger an output, a coil has to be energized where that coil intact or in turn breaks or makes a contact. Controller binary outputs can be used to trigger external relays which are high amp rated for different loads. Consider if there is a lighting load, you might need, depending on what light loads or how much light loads it is, you might need a whole new contactor which is rated for higher amperage, which your controller cannot suffice. So you will have to use your relay output to trigger another contactor, which in turn turns the lights on and off. Apart from these, the other thing which we wanted to discuss, or which we can discuss in the binary outputs, is VAV applications usually use floating outputs instead of analog outputs. The difference between a floating output and an analog output is your analog output is control signal, which is a DC voltage signal varying from 0 volts to 10 volts. Floating outputs are two binary outputs controlling a damper actuator for the VAV, which can still be acting as an analog output. So the way it works is a floating output with two outputs, which are one for open and one for close. Every actuator of that particular VAV has a drive time, which is a constant drive time. Say it is from the 0 degree, if it has to go to 90 degrees, it has a runtime of say 100 seconds. So if you want to control your damper at 50%, so all you have to do is turn on open output for 50 seconds, which turns the damper to 50%. Now, if you turn it off, it's not going to go close because you have an other output which is close. So if both the outputs are not active, it is going to stay in the last position it was. Now, if you want to close it, then you'll have to trigger the close contact for another 50 seconds to come back rest in the zero position again. That's how the wavy floating output actually works as an analog output, but with the use of two binary outputs. Now, that's pretty much how a binary output can be used as an analog output only in the case of VAVs. There are a couple of actuators which are used for the reheat valves as well, which takes a floating output as well. So whenever you hear floating output, it is considered to be two binary outputs which is being utilized in your DDC. So let me demonstrate to you a quick field setup of how things work with binary outputs. So for the binary outputs, I have a little demonstration of a single controller and a functional device relay, which is a 24-volt relay. So all we have done is this black wire here, which is a 24 volt going to a relay, and the white and the blue coming back to a relay here, and white and yellow is the common. So this is a contact which is being made once we energize this relay, which you can see this is not lit, which is going to be lit once we energize the relay here. And the orange and the yellow cables which you see is nothing but the binary inputs again, which in turn, when this is an external relay, while this relay is triggered, it in turn triggers this relay, which makes or breaks the contact between these two, where an external load is considered. So let me go and energize this relay here, where you can see this relay being lit. So as this relay, and which was a normally open contact, was made, and you can see this making a contact here. So if I release this back, you can see this relay going off, this relay going off, and the contact being open here. So this is a setup for a floating actuator demonstration. So all I here have is a floating actuator which has three leads, white, a blue, and a red, where red is the common, which is going to the common of the actuator. Blue is one of the outputs, which is to digital output 2, and white is another output, which is to digital output 1. So what happens here is when I press digital output 1, this is going to bring this little red red dot you see here. This is going to bring down, in turn, it is going to push the stem down of the valve where there is flow, and it is going to retract back whenever DO2 is energized. So let us quickly see that happening with me energizing DO1. Now you can see this going down, further down, as much as I have DO1 energized here. So once I release this and say, hey, bring on DO2, which is currently turned on, this is going to bring that stem upwards. It is a long process. This actuator takes almost 90 seconds for a full-fledged up and down motion, so you can minutely see that. I'm not sure if I can capture it better in the video here though. So as you see, the stem is moving all the way up. And that's how a floating actuator acts as an analog actuator with two binary outputs. You can see the stem all the way up right now. So now that we have completed analog outputs, binary inputs, and binary outputs, I just want to throw a quick note that I have been developing an Excel-based solution tool for Tritium products where you can throw in your number of controllers being used, number of points which you're using, a draft design architecture of how we want to, uh, or how many controllers and how it is spread throughout your building or throughout your architecture. And it can give you a auto-generated bill of material with cost-effective options. All you have to do is put your number of controllers. If it is IP, is it MSTP? Where is it being controlled? Or where is it being connected? Have a draft architecture design made from the solution tool, and you don't have to worry about how many licenses should I take, what license should I take, what are the protocols I have to include, what and all do I get, what and all do I lose, how do we do this? All that has been implemented in the solution tool. So I'll be doing a demonstration of this tool in my next video. So stay tuned, and hopefully you'll like the tool. Let's see how it goes in the next video. Please drop your comments of what you think of this video, what you guys have any suggestion, if any. Uh, Thanks, guys.